Hey guys, welcome back. So this is the fifth video of the series. It's the second fundamental theorem of calculus, where I'll be explaining the difference or the two reasons why we use the second fundamental theorem of calculus. So good luck, and here we go. Okay, so let's get started with the second fundamental theorem of calculus. So here we have a definite integral. We have a lower limit, we have an upper limit, and those are constants. And then, of course, we have our function of x, and of course, dx. Now, if we did not have the constants, in other words, if we did not have our lower limit or upper limit, then we would have just the basic integral, which we call the indefinite integral, and we would use that to find the antiderivative. Now, what I want you to notice, what's on the screen, is that the upper limit is x. So f as a function of x. And instead of anti-differentiating with respect to x, we're anti-differentiating with respect to t. So those are the major changes that are going to help us with the second fundamental theorem of calculus. Now, this interpretation of an integral is called an accumulation function, and it is used in the application of integrals, which we'll see later on in other videos. But it's known as an accumulation function. So what this allows me to do, it allows me to find a function, and then therefore I can choose arbitrary points between my interval, my lower limit and my upper limit, to be able to find the area underneath the curve. So for example, I can choose an arbitrary point, in this case x1, and I would be able to find the area between a and x1. Or I can choose another value, in this case x2, and I would find the area underneath the curve between a and x2. So what this does, it allows me to accumulate the areas underneath the curve, depending on which arbitrary x values I choose between a and b. But in the end, it allows me to find a function. And what do I do with this function? I can replace values of x and find the area underneath the curve. Now, the actual theorem itself for the second fundamental theorem of calculus is this: that if we take the derivative of the antiderivative, where the upper limit is a variable, in this case x, then what I will end up with is simply f of x. And we've seen this before. So the derivative of the antiderivative is equal to f of x. So the fundamental theorem of calculus is used for two main reasons. One, to show the relationship between the antiderivative and the derivative. And number two, it's for accumulation functions. And we'll see both these examples in the following slides. Okay, so let's take a look at an example. So here I have technically the second fundamental theorem of calculus, where it's taking the derivative of the antiderivative. And I already wrote the answer down, which is simply the square root of x squared plus 1. But my function was t squared plus 1. Well, all I did was I simply replaced t with the variable x, with the upper limit x. Now, this is quite simple. But why is this the case? Why does this happen? It doesn't happen all the time. But when a specific upper limit is simply the variable x, I can simply substitute the t with the variable x. However, we're going to do this the long way. So the first thing we're going to do is we're going to integrate to find the antiderivative as a function of x, and then we're going to demonstrate the second fundamental theorem of calculus by differentiating what we found in a. So, example. The antiderivative, or the definite integral, of t plus 2 dt from 0 to x. Okay, technically, if I were to follow the previous example, then my answer would be really simple, would simply be x plus 2. But let me show you why this is the case. So we're going to evaluate this definite integral. So we find the antiderivative, which is t squared over 2 plus 2t, and we're going to evaluate between 0 and x. So how did we evaluate definite integrals? Well, it's going to be the upper limit, f of b minus f of a, same concept as previously done. And we get x squared over 2 plus 2x minus 0 plus 0. So if I were to take the derivative of the antiderivative, so in other words, the derivative of x squared over 2 plus 2x, I would end up with simply x plus 2. So you see, this is quite simple. All I really needed to do was simply replace the variable t with x, and I would have found my, or I would have used the fundamental theorem of calculus in one step. Okay, so let's take a look at some examples. Integrate f as a function of x. That's the question. Now, normally when you see this question, you think first thing, second fundamental theorem of calculus. So we have this definite integral, and we have the function t times t squared plus 1, and we have the lower limit, which is 0, and the upper limit, which is x. Well, what I'm going to do is I'm going to rewrite this, and I'm simply going to distribute the t to end up with t cubed plus t dt. Now, according to what I taught you previously, you should just look at this answer and say, well, it's just replacing t with x, and there we go. So the antiderivative of t cubed plus t dt is simply x cubed plus x. Now, let me show you the long way. If we did it the long way, then once again I would have to find the antiderivative of t cubed plus t, which ends up being t to the 4th over 4 plus t squared over 2, evaluated from 0 to x. Now simply f of b minus f of a, and I get x to the 4th over 4 plus x squared over 2. If I were to find the derivative of x to the 4th over 4 plus x squared over 2, I would simply end up with x cubed plus x. Hopefully this makes more sense. As you can see, using the second fundamental theorem of calculus, we can simply do a direct substitution to get our answer, or of course, if I always want to check my work, I can do this the long way. Okay, so this is the second example. Once again, the similar question. Integrate f as a function of x means use the second fundamental theorem of calculus. And what we've learned previously, we have the square root of t, so therefore my answer should really be simply the square root of x. Done. There's my answer. I used the second fundamental theorem of calculus, and that's what it works out to be. However, let's do it the long way. So once again, I'm going to find the antiderivative of square root of t, which is simply 2 times t to the 3 over 2 over 3, evaluated from 4 to x. Once again, f of b minus f of a, evaluate, and simplify. Now, I need to find the derivative of what I just found. So we're going to find the derivative of this, and I end up with x to the 1/2, and we know that x to the 1/2 is simply the square root of x. So all of this work is simply replaced by doing a direct substitution, whereby we change variable t with variable x. Now this works when we have a constant in our lower bound and a variable x in our upper bound. As those variables, or as those upper and lower bounds change, well, then we need to modify a little bit how we use the second fundamental theorem of calculus. But in the end, all this tells us is that there's a relationship between the derivative of the antiderivative and my original function. Okay, so we have this antiderivative, we have this function f of t dt, and of course we have from the lower limit, which is normally a, which is a constant, to my upper bound x, which is a variable. Now, any upper bound other than x requires the use of the chain rule. So in other words, let's say you were looking at this particular question, and now your upper bound, instead of being x, is x squared. Now you'd have to use the chain rule. You cannot use direct substitution. However, there's a better rule. There's an easier way of using the second fundamental theorem of calculus, but instead of using the chain rule, we're going to use this specific formula. So what I want you to do is pause the video, write this down, and you'll see how useful this formula is. What I want you to notice is that the lower bound is g of x, which technically we consider that as a function, and h of x, same idea, as a function. Now, g of x doesn't necessarily have to be a function, it can also be a constant. This formula applies to all scenarios, even the one whereby my upper limit is simply x, and I'll show you an example of that after. So, let's take a look. We have the question from the previous example, the previous slide that we saw, is from 0 to x of x t cubed plus t dt. Now normally, because the upper limit is simply x, I would simply replace t with x, and I would end up as an answer of x cubed plus x. However, we're going to use this following formula. Now hopefully you remember how to compose functions. So f of h of x means I'm going to take h of x, in this case x, and replace it into my function, so it becomes a direct substitution. Then I'm going to multiply it by the derivative of h of x. So the derivative of x is simply 1. minus f of g of x, meaning I'm going to take my function g of x, in this case it's 0, and replace it into my function. I get 0. And then finally multiply by the derivative, and the derivative of 0 is simply 0. What do I end up with? I simply end up with x cubed plus x. So this formula not only works for definite integrals whereby my upper bound is x, but normally we would simply use this formula. We would replace the chain rule with this formula to evaluate when my upper limits are values or variables other than x. Okay, so let's take a look at the next example. Find a derivative of this definite integral evaluated from pi over 2 to x cubed. Oh, the upper limit is x cubed. So now I gotta use the formula that I gave you previously. So we know what h of x is, we know what g of x. So what we're gonna do is simply identify it. So h of x is x cubed, g of x is pi over 2. And we're simply gonna apply the rule f of h of x times the derivative of h of x minus f of g of x times the derivative of g of x. So when I simply plug and play, I end up with cos x cubed times 3x squared minus 0 times 0. Final answer, cos x cubed times 3x squared. Done. If you had to use the chain rule, it's a little bit more complicated. It requires a little bit more steps, but I think that this formula is the best way to evaluate the second fundamental theorem of calculus, especially when your upper limit is something other than x. So now, let's put it all together. Let's try to understand the second fundamental theorem of calculus and the relationship between the derivative and the antiderivative and, well, the function itself. So let's take a look. We know that the derivative of the antiderivative, especially when my upper limit is x, is simply f of x. Great. We also know that if we take the derivative of the antiderivative, we end up with f of x. So let's take a look at an example. I have this function t squared dt between 0 and x squared. I find the antiderivative, and I evaluate this definite integral between 0 and x squared. I end up with f of b minus f of a, and I end up with x to the power of 6 over 3. Okay, now that's done. Now what is this? This is my antiderivative. Now, if I were to take the derivative of the antiderivative, I would end up with 2x to the fifth. Now, what is 2x to the fifth? 2x to the fifth is simply f of x. So the derivative of the antiderivative is simply f of x. Great. However, if I were to take the antiderivative of my function, I would end up with x to the sixth over 3, which of course is the antiderivative. Look at that, it's the same. And if I were to take the derivative of that, I would end up with 2x to the fifth. So you can see that there is a direct relationship between the derivative and the antiderivative. And that is really one of the reasons for the second fundamental theorem of calculus, is to show that relationship. The second reason, you'll see in the next slides, it's about accumulation functions. Okay, we're going to take a look at some practice examples just so that we can distinguish between the first fundamental theorem of calculus and the second fundamental theorem of calculus, or for example evaluating simply a definite integral. So we have this function, or we have this integral. It's a definite integral because we have our upper and lower values. We know that it's from 2 to 5, so therefore it is simply a definite integral. It's dv, so therefore it's with respect to v. So all I need to do is simply find the antiderivative, and then I'm going to use the fundamental theorem of calculus, or the idea of evaluating a definite integral, and do f of b minus f of a, evaluate, and I get negative 39 over 2. So question like this, very simple. I'm just simply evaluating the definite integral, and I'm using the fundamental theorem of calculus, or the first fundamental theorem of calculus, to do so. Next, if I'm given a graph and I'm given a function and I'm asked to evaluate, well, this is quite simple. I know that my lower bound is 1, my upper bound is 2, and I have my function 1 over x squared. So simply write down the definite integral of 1 over x squared dx from 1 to 2. Okay, Now, what may happen sometimes, especially using the fundamental theorem of calculus or working with the fundamental theorem of calculus, you'll end up with this definite integral whereby my lower limit is negative x and my upper limit is simply x. So there's a way we rewrite this. So if I were you, simply pause once again, write this down, and you'll see that all we're doing is we're replacing the a and b, interchanging them, by bringing the negative forward in front of the integral sign. So in other words, I have negative 0 to x f of t plus integral 0 to x f of t. So just keep this on a side note because you can see that sometimes we might be able to use this. Okay, so let's take a look at a third example, and this one says find the derivative of the antiderivative. So that automatically means use the second fundamental theorem of calculus. Also, notice that the lower bound is negative x, the upper bound is x, so already we have two different functions, h of x, g of x, and it's of course d of t, t cubed, so I know that I have to use the second fundamental theorem of calculus. So, once again, how do we do this? Well, because I'm running from negative x to x, what I'm going to do is I'm going to rewrite it using that note that we saw in the previous slide. So I end up with negative the integral from 0 to x and then from 0 to x. Now remember that when I take out the negative, I can rewrite or rechange or change a to b, b to a. Okay, so that's why I pulled out the negative, and by doing so I interchange the a and the b, and I always want the lowest value in the lower sum or in the lower limit, and I want of course the variable in the upper limit. Now according to what we did previously, since it's simply the upper limit is x for both cases, I just simply replace with x, and I get negative x cubed plus x cubed would equal 0. Now what does that really mean, equals 0? Well, let me explain this to you. The negative area cancels with the positive area. So in other words, the negative area between negative 1 and 0 cancels out with the positive area between 0 and 1. So that's why when we go from negative x to x, we end up with a definite integral that has a value of 0. This is really what 0 means. It means that the areas canceled each other out. Okay, in this example, I'm going to show you how we use the second fundamental theorem of calculus as an accumulation function. Hopefully by the end of this example, it should be quite clear on what we mean by an accumulation function. So let's assume we have this particular question. Find the definite integral. My upper limit is x, so I know I have to use the second fundamental theorem of calculus. I simply find the antiderivative. I evaluate, and I come up with this particular rule. Now, x squared minus 2x is a general rule to allow me to find areas underneath the curve at arbitrary x values. So in other words, if I have this graph and I was looking at x equals 2, then technically my definite integral would be from 2 to 2. And we know that by definition that I'm not really going anywhere, so the area underneath that curve is going to be 0. Now, I can choose another arbitrary point, and in this case they're asking me to find 5. So at 5, when I look at the graph, I'm finding the area between 2 and 5. And the area under the curve between 2 and 5 is 15. And then finally, I'm asked to find that x equals 8. And when I take a look at the graph from 2 to 8, I have an area of 48. So what does this mean exactly? It means that I can find the area or the accumulated area underneath the curve depending on which x values I want to take a look at. So between 2 and 2, well, it was 0. Between 2 and 5, the area was 15. And between 2 and 8, the area is 48. So I could use the second fundamental theorem of calculus to find this general rule, x, and therefore put arbitrary x values to find the area underneath the curve. However, what this really means is simply finding the integral, or the definite integral, between 2 and 8 of this function t squared minus 2t. And when I find the definite integral, and I evaluate using the first fundamental theorem of calculus, I end up with an area of 48. As you can see, those are similar. So it is an accumulation function. So I come up with a function, and I can therefore put arbitrary x values and slowly accumulate the values or the area underneath the curve. And if we take a look at it this way, broken down, if I find the area between 2 and 5, and then I find the area between 5 and 8, I end up with 15 plus 33, and that works out to 48. So hopefully this clarified the second fundamental theorem of calculus when we talk about accumulation functions. Alright guys, like always, last but not least, practice, practice, practice. It's extremely important that you look at some examples, especially you can go online. There's thousands of examples of using the second fundamental theorem of calculus. Very important to practice and very important to understand exactly why you learn this. So, once again, second fundamental theorem of calculus, number one, known as an accumulation function, and number two, to show the relationship between the antiderivative and the derivative. Hope you enjoyed. Be safe.